Good afternoon, everyone. Yeah, it's my great honor to introduce our very popular speaker today. Yeah, Professor Marco Pavone. So, even though he's still very young, look at him. Professor Professor Pavone has a very distinguished career in both academia and industry. Excuse me. So he got his PhD from MIT in 2010, and then right after he joined the famous JPL lab, Jet Propulsion Lab at Caltech. A few years later, he joined Stanford University as professor of Aeronautics. Professor Mark has won many prestigious awards, including the PCAS Presidential Early Career Award for scientists and engineers from President Obama. And he has won many other career awards, like ONR, Navy Office of Navy Research, and NSF for Career Award, NASA Early Career Award, and also has one teaching award. So without further ado, please join me in welcoming Professor Pavone.
Hi, it's a pleasure to be here and to talk to you a little bit about my work on autonomous robotics. In particular, I'm going to talk about some of our recent work on leveraging generative AI technologies, in particular foundation models, for the faculties of AV development. So what I will be discussing today is how these new technologies provide new opportunities to rethink how we can develop autonomous vehicles. Now, the premise, I think I have to do it myself. It's okay.
It doesn't work.
Doesn't work. No, okay, that's fine.
Okay.
So, yeah, so we'll say the premise of this talk is that generative AI is, of course, changing the way we work and we seek out knowledge. For example, large language model can write the code for us. And the emergence of such capabilities is so profoundly revolutionary that people refer to it as the iPhone moment of AI. Now, broadly speaking, the main reason for such an acceleration has been the advent of foundation models that essentially have shifted out from a paradigm of machine learning models for specialist tasks toward a paradigm of general knowledge acquisition. And here I want to be a little bit specific of what I mean by foundation model. By a foundation model, I mean a model that has been trained on raw data, typically at the internet scale and in a self-supervised fashion. They can then be adapted or fine-tuned to a wide range of downstream tasks. Popular examples of foundation models include large language models, visual language models, video generation models, and so on and so forth. Now, we're not quite there yet at the level of one giant model that can ingest any data modalities and it can be fine-tuned to any possible task. But this idea of pre-training at a very broad scale and then fine-tuning to downstream tasks has proven useful to in a variety of different domains, to the point that oftentimes when we play with such models, we have the explanation, wow, I didn't even know that such a model could do that. So it's tempting to say that AI, in particular generative AI, makes everything better. So let's apply it to autonomous vehicles. Well, before we do so, we have to properly contextualize in what ways generative AI can help the development of autonomous robots. We don't just want to jump on the bandwagon because there is a lot of hype behind this technology. And indeed, the AV technology is already quite mature, with robotaxis driving around, for example, in the city of San Francisco as we speak, and very advanced driver assistance systems becoming very popular with a number of automakers. And so far, this has been enabled by the judicious incorporation of specialist machine learning models in the AV stack, like for example, for the purposes of perception or projected recognition. But these systems still miss the mark in the long tail of situations that a vehicle can encounter. For example, an autonomous vehicle can still get confused by new deployment domains, like for example, adversarial weather conditions, optical illusions, like for example, in this case where we have a truck that is transporting some traffic lights that could be mistaken by illegal traffic lights. Or for example, here I don't even know what this is exactly. It's basically a giant inflatable minion that is in the middle of the road, and somehow the vehicle should be able to reason about it. So now it's useful at this point to wonder how we as humans navigate the long tail of events, so all these difficult corner cases. Well, as humans, we bring to the task of driving a lifetime of experiences beyond driving. It is very useful to endow us with the generalization capabilities that are needed to reason about those corner cases. Analogously, the hypothesis is that foundation models, which have been trained on multiple lifetime of experiences, both from the driving domain, but crucially also from a non-driving domain, give us an opportunity to endow autonomous robots with a level of common sense reasoning, or at least contextual understanding, to properly assess this complicated situation. Or at least this is the hypothesis. Now, the question is how we can access this generalized experience for AV applications. And the answer is in multiple ways. As I discussed in the rest of the talk, foundation models can be used to empower several aspects of AV development, from offline development processes such as simulation, auto-labeling, data curation, scenario generation, and so on, all the way to the onboard stack. So the point here is that the foundation models can empower really the full development problem. Typically, people focus on the onboard stack. It's probably the most exciting part. But foundation models can actually help across the board, also in terms, for example, of data curation, which is a very crucial aspect. Of course, safety is a common concern. So there are a lot of concerns in the community about how we can field the foundation models in a safety critical context, such as self-driving cars or maybe autonomous spacecraft. And as I'll discuss at the end of the talk, we do indeed have several tools to keep the AI in check. So we have a way forward. But at the same time, I will also discuss how foundation models provide opportunities to make a self-driving car safer, for example, by providing us with an opportunity to build semantic, more powerful runtime models. So what I'll do in the rest of the talk is first to talk a little bit about key considerations to stand up foundation models specifically for the purposes of AV applications. Then I will discuss how foundation models can be used throughout an AV development program, focusing on the simulation on the offline part, and then on the onboard stack. And finally, I will wrap up the discussion with an overview of our work on safety, particularly in the context of runtime finders. So let's start with the topic of building foundation models for autonomous vehicles. So at a high level, there are three core choices underpinning the development of foundation models for robotics or autonomous vehicles. Namely, the choice of data, the choice of the model, and the choice of training tasks. So for data, we typically use multimodal data, such as camera or LiDAR data, or vectorized data, like for example, maps, or even intermediate representations, such as BEV features. In terms of models, there are a few options. For example, auto-regressive models that are more common in the large language model domain, or diffusion models that are more common in the video generation domain. And then for training, as also mentioned before, we split training into pre-training and fine-tuning. In reality, there are additional phases referred to as post-training that I will skip here. So for pre-training, we aim at considering tasks that can scale all the way to internet scale. So what are the two data modalities that are available on the internet? Text and video. So accordingly, we have large language model and then video generation models. And then for fine-tuning, we use we consider specific A/B tasks of interest, like for example, trajectory generation on a detection, which we supervise during the fine-tuning stage. Now, what's the idea behind the pre-training a model with the language? Well, the idea is that in that way, you gather some sort of common sense reasoning capabilities that could be useful to reason about rare cases. But video generation models, you acquire a very strong visual representation on top of which you can then add the policy and for plans. So this leads to essentially the two main categories of foundation models that are used in robotics in general, autonomous vehicles in particular. The first category is referred to as multimodal large language model. Well, as the name suggests, the main pre-training task is that of language generation. And so multimodal language models are actually a very prominent model in the field of robotics. And here I just show you an example of what we've been doing with these models. For example, in the context of a co-pilot. So think about yourself driving around, and then you are confused by a situation, by, for example, a traffic sign, and then you ask the machine, the car, to explain to you what you should be doing. And so this is a case which we took from a state in Mexico. As you can see, it's a bit counterintuitive because you have arrows that are telling you to go into the opposing lane. So the idea here is that you ask a multimodal LLM what's going on, and then this is actually the output. Just as an example, I mean, many more examples are available in the paper here at CVPR, where the model has enough understanding to tell you, well, this is a particular traffic arrangement in Mexico that is telling you to drive on the opposing lane to have better visibility about the upcoming line corner. So a bit confusing rule of the road, but anyway, so here the point is that these models have the capability of processing this type of difficult situations. And we'll come back to multimodal language model later. Here's I want to turn attention to video generation models. So while large language models have been around now for the past 3-4 years, video generation models are comparatively more recent. They became quite popular last year with the advent of Sora, which is a video generation model out of OpenAI. And now there are a few around. For example, NVIDIA has its own video generation model that is called Cosmos. As the name implies, video generation models are foundation models where the task is that of video generation. And as an example of video generation model, here I present one of our latest token-based multi-view video generation models. Our models take inspiration from Gaia 1, which is a video generation model that has been developed by a company in the UK called Wave, where the video generation model is turned into a conditional sequence prediction task, very similar to what you do with a large language model. And while this approach sounds conceptually similar to the one of Gaia 1, actually we made a number of advancements, one of which is that of being able to generate videos from multiple viewpoints, essentially mimicking the different cameras that you might have on an autonomous car. So these models are promptable. So here, for example, we're showing some input prompts. We ask the AI model to generate a scene of a car that is driving around in a wintry condition. And then the model generates all these videos from different viewpoints in a consistent way. For example, you can see that this car shows up with the shadows into the center view. So all of this is generated by the model. This is a scene that never existed. And so this is another case of a video generation model where we generate traffic. You can see how there are also interesting lighting effects. Of course, you're not confined to 3 cameras. You can consider 6 cameras. And for example, this is a video generated by a model of a highway. Of course, the models are not perfect yet. So for example, I focus here on what's going to happen in this square. There's something funny that is going to happen. So you see the motorbike is appearing and then it's disappearing. So this is a so-called hallucination. So this model, for example, still have an issue with the object appearance. And one of the reasons here is that the model during training was not really exposed much to motorbikes. So now the jury is still out in terms of which model is best at what. Video generation models, first of all, can be very useful for simulation, obviously, because they allow you to generate data against which you can drive. But at the same time, as I mentioned before, if you really can generate a video for multiple seconds in the future, it means that the model has acquired a very strong visual representation of the work. And that can become the starting point to build a powerful driving policy on top. On the other hand, multimodal and language model, which are grounded in language, so in principle, they have seen all possible logical pathways someone could exercise, have the potential to be very good listeners. And I will provide a little bit more evidence for these statements later on. But for now, let's turn a little bit attention to how foundation models can be used as part of an AV program, starting from the topic of offline processes, in particular, simulation. So simulation is an interesting topic in robotics and autonomous vehicles in general. Of course, if we had a good simulator, then the cost of development of robotic systems will be dramatically reduced, and the timeline to develop the systems will be dramatically accelerated. The reality is that simulation is not used much, or at least it's not used as much as we would like in a production setting. So the typical simulation that is used, for example, in autonomous driving, it is referred to as log replay. So essentially, people record a drive, and then with the test vehicle. And once you have a new model, a new prediction model, a new detection model, then you rerun the new detection model along this recorded drive, and then you see whether some metrics improve. Like, for example, with new detection algorithm, maybe you can detect some objects a bit better. Now, this works well, for example, for perception networks. Doesn't really work well when you want to test new policy planning algorithms. Why? Because if you have a new policy to drive your vehicle, then your vehicle might decide to change trajectory with respect to the one that has been recorded. But all the vehicles around you are just going to be replayed. And so basically, the simulation doesn't make sense anymore because, of course, the other vehicle will have reacted with respect to your new maneuvers, but that is not captured by the simulation. I would say that until 3-4 years, we were pretty much stuck with the log replay. But fortunately, in the past 3 years or so, there have been a number of advancements that have dramatically improved the state of simulation. And one of these advancements is represented by neural field representations, such as, for example, nerves, which have emerged as a very powerful tool for scene reconstruction and representation. So here I show our recent work, Nerve, that decomposes the complex scene into its static background, dynamic objects, as well as optical flow. And it can do that in a completely self-supervised fashion, so without the need for human levels. And the reason why these models are interesting for the purposes of AV development is that once you can reconstruct a scene, then you can imagine driving along the scene, but from a different viewpoint or from a different initial position. Like, for example, here, in this video, I'm showing you the camera log as recorded by a test vehicle. And here I'm going to show you at the bottom a re-rendered video from a different viewpoint that has never been seen during the recording time, and it is generated by the neural network that has learned how to represent this scene. So this is a reality, and this is a simulation. You see that we follow a different trajectory relative to the one that was recorded in the real life. So here you see how we have dramatically improved visual realism. But first, before I was saying that it's a problem that the other vehicles around us around us do not react to what we do, we still have the problem here. So all the vehicles here are still being replayed in this reconstructed environment. So that's still a problem. By the way, we can also reconstruct not just images, but for example, also point clouds. So to address the problem of behavioral realism, in my work, with my group, we've done a lot of work on building data-driven traffic simulators. So basically models that learn from data how humans drive, and then you can use these models to simulate reactive traffic. And then you can blend neural representations with behavioral models to now have reconstructed scenes from different viewpoints or on different trajectories with traffic that they have related to what you do. So that's great because we have dramatically improved both sensor realism, visual realism, and behavioral realism. But there is still a problem that, and this is something that I also discussed this morning with some of you, that creating scenarios that are useful for the purposes of redevelopment of testing is difficult. Of course, most of the driving is boring, it just goes straight. You're interested in creating scenarios that are challenging and can stress test your system. So that's a setting where foundation models can really help. In one of our recent works that is called LCT-Gen, we use a text interface to control both the initialization of a scenario and also its forward evolution. And here I show you some examples whereby we start from an input scenario and where then with a text interface, we ask the model to recreate the different scenarios and evolution. Like for example, make one of the car go to the left. Here you can see how this reconstruction process is dynamically informed, in the sense that we ask the model to speed up all the cars, and the model correctly places the blue car over there on the other lane, because by speeding that up, then the blue vehicle would otherwise react with the red vehicle. So when this becomes very powerful is that, of course, we can condition the generation in all sorts of text data, including, for example, police reports. So what we did was to take all the crash data reports that have been recorded in the NHTSA SAREN database, and then used this machinery to generate scenarios that represent those crashes that have really happened. Of course, the police reports tend to be quite sparse. There is some information about maybe two vehicles closing in at a speed of 30 miles per hour or so. Then we use generative AI to augment those reports with physical assets, like, for example, other vehicles on the road or crosswalks and so on and so forth. So this is an important technology because it allows us to ground the scene generation into plausibility, where plausibility is because the initial condition of all these scenarios is a case that has really happened. And of course, you can randomize to get additional cases. So a little bit more in detail, the way that this tool works is by first converting a given scenario prompt into a structured representation, a detailed version of which you can see here. And then this representation is taken as an input into a map retrieval framework that is then used to generate the full scenario along with this, its evolution. So I like to refer to this as generative AI at its finest. It's not just a text to image, it's not text to video, we say text to closed loop simulation. And we have also made some refinements. One of our recent work, ProSim, what it does is to be a much more flexible, frontable interface where we can generate a scenario not just with a text prompt. You can certainly use that, but you can also sketch some trajectories that you want some of the vehicles to drive or some goal conditions. So it makes it very easy for the designer to come up with scenarios of interest. So putting everything together, we can combine the scene reconstruction pipelines with the capability of generating targeted scenarios via a language interface to create in a very effective way difficult situations for vehicles that can be used both for validating an autonomy stack or to help with training. So here, for example, I'm showing you a case about how we use this tool chain. At the top, we have a video of a car. So this is a real video that stopped at the stop sign. So it did the right thing. But now we're interested in generating a similar scenario where we ask the simulator to generate a scenario whereby the black vehicle drives erratically. So it doesn't stop at a stop sign or drives recklessly. So we do that. And at the bottom, you see the new scenario that is resimulated. So this is a scenario that has never happened. Has been recreated by the AI model, whereby the AI model basically removes the black vehicle from the scene, reconstructs it, places back the black vehicle, and then decides to let the black vehicle speed through the stop sign, essentially emulating a scene whereby we have a car that is not paying attention to a stop sign. So of course, the point is that now we can do this at scale. We can generate thousands of these scenarios with a very flexible, programmable interface in a way that is visually very good. So this is all good, but there is a catch. So underpinning all of this is, so we use neural reconstruction techniques. And what neural reconstruction techniques is to reconstruct. You give them a recorded video, and then they reconstruct that video. And then they can generalize the reconstruction from, say, different viewpoints or different initial conditions, but up to some limit. If you, for example, change your position by, say, more than 5 meters with respect to the one that was used during recording, then the reconstruction starts basically failing. And here I show you one example. We're driving in a neural reconstruction-based simulator. Then the simulated vehicle is doing a U-turn, and when it's doing the U-turn, you start seeing a lot of artifacts, all those gray blobs and stuff. That means that the neural network that was trained to reconstruct the scene has basically reached its boundary of generalization and start just spitting out random information. And of course, in general, with the 3D construction pipeline, you cannot generate scenarios that are completely different from the ones that you use for the construction algorithm, which is a problem because in some cases you want to generate scenarios that are very, very bizarre, and maybe you don't have any data supporting them. Well, so given everything that I've said before about video generation models, then one idea would be to say, well, just take a video generation model and use that to generate your crazy scenario. Well, but as I said before, the problem with video generation models is that they can hallucinate, they can create artifacts by themselves, which, strictly speaking, make them not immediately applicable to A/B testing application, for example. So what we've done in order to address this challenge is essentially to bring together the two streams of research from neural reconstruction, like for example, nerves and Gaussian plotting, a video generation, into a combined framework, which we call the Dream Drive, that tries to get the best of both worlds. So essentially the generalization capabilities of video generation models with the geometric accuracy of 3D for the reconstruction pipelines. So what we do is to start from an image of the world and use it as the prompt for a video generation pipeline, like for example, coffees. And we generate a video of a scene, and I'm showing here one example. Note that, for example, so this is the output of the video generation process. Notice here, we start seeing some hallucination. So you see how this grass is changing color from green to brown, which of course to you as a human doesn't make any sense. You know that the color of the grass should be persistent over a couple of seconds. So this is an hallucination of the video generation model. But then what we do is to feed this video into a neural reconstruction method to produce a 4D spatial-temporal representation of the environment. And you can use different reconstruction pipelines. And once you've done that, then you can drive through that 4D representation. And what that 4D reconstruction step does is basically to bring geometric accuracy to the simulation. For example, here you see that now the color of the grass is much more consistent. So this is just one way of blending together reconstruction techniques with the video generation techniques. I think there is a lot of potential in finding even deeper ways to bring the two together. Again, they have a complementary advantages. What we're trying to do here, as a takeaway message, is to get the best of both worlds. All right, so let's move on then to the topic of using foundation models in the context of onboard autonomy. So basically to improve the decision-making processes on the vehicle itself. Now, as I said before, foundation models have the promise to allow us to drive better through more generalization capabilities. But the question is, do we have any evidence for that? Makes sense, but do we have any evidence? So to address this question, we had an investigation last year where we essentially studied the problem whereby we view a large language model as essentially an embodied agent that calls on demand different capabilities such as detection or trajectory forecasting or planning in order to solve the driving task. And we use text as an interface between all these different modules, since everything is orchestrated by a large language model. Of course, this is not how you would architect things on an autonomous car. It wouldn't be very efficient from a computational standpoint. But here the idea was more to understand whether large language model had the potential to drive better. And the end result is essentially shown here by this plot. So on the x-axis, I show the percentage of AV-specific data that is needed to train a model. And on the y-axis, I have the different metrics. So for example, how well we track the center lane of a road, or how far we stay away from other vehicles, and so on and so forth. And we compare the LLM-based driver, which we call agent driver, to the best academic model available in the literature at the time, called UNI-8. And the bottom line is that with only 1% of the specific data, agent driver already outperforms the best academic model out there. And of course, with more data, it gets even better. So what's the catch here? So the reason why agent driver only needs 1% of the specific data is that it effectively leverages all the knowledge that it has acquired during the pre-training at infinite scale. So indeed, the language pre-training helps, and that knowledge can be reflected into the task of driving to the point that we only need 1% of the specific driving data. That's a big deal. And this specific data is very expensive. You need a fleet that acquires the data for you. So this was in the context of LLMs. We have also done similar work in the context of vision language models and corroborate the message that the language pre-training helps. So motivated by this evidence, then we started wondering, well, so if vision language models, for example, help, what is the best way of using them in a stack? You can use them in many different ways. You can use them as the main backbone for your architecture. You can use them as a sort of a substitute for your mission planner, for essentially the module that tells the vehicle whether it should change lane or it should go straight and so on. You can use them as a runtime monitor, so basically as something that checks that your autopilot is doing something meaningful. There are many different ways you can use them. What is the best way to do so? So taking a step back, so this is a question of system architect. So how do you architect an autonomy stack, which is one of my favorite topics. And in general, in the literature, there are two main paradigms. The first one that is the most classical, and to this day, the one that is most used is referred to as modular AV architecture, where you have an architecture that is highly modularized. So you have, for example, a control module, a detection module, a trajectory forecasting module, a tracking module, planning module, and a task planning module, and so forth. And this is the most classical architecture for an AV stack, and it makes a lot of sense. Is easily debuggable, it's very interpretable. Even organizationally, it helps because you can map your entire organization into a mapping module, a detection module, so it also helps from a project management standpoint. So of course, when you put everything together, you have integration challenges, obviously. And also, since the stack is so modularized, it cannot be end-to-end optimized. So you are basically leaving some performance. So this motivated people in 2017 or 2018 to consider fully end-to-end AV architectures. So the idea was, well, why don't we just replace the entire architecture with a giant internet network that maps inputs into like images into outputs, like for example, steering control of hardware command designs. In principle, it's a great idea because, of course, such an architecture can be end-to-end optimized, so it can achieve a level of performance that would be superior to a modern architecture. But such an architecture is very difficult to debug, to maintain, to reuse, and so on and so forth. But in the past few years, thanks to advances, for example, in optimization and differentiable algorithms, a third paradigm has emerged, which I refer to as a differentiable and modular architectures. These architectures that have a few modules that are fully differentiable so that you can actually propagate gradients from the output all the way to the input. They try again to get the best of both worlds. The end-to-end optimization properties of end-to-end architectures with a level of insight or introspection you can get from a modular architecture. So I view these two paradigms as two ends of the spectrum, and there is a lot of things in between. And now there's been a resurgence of interest in architectural topics, and people are publishing a lot of papers on how you can, select different modules and so on and so forth. In other words, the design space. So if I convince you that this is an interesting paradigm, now the design space is huge, and in particular, the design space has three main dimensions. The choice of modules, so which modules do you want to have represented in your architecture? The choice of information representation, how do you want to represent the information in between modules? Like, for example, do you want to represent a map through a VV map, so essentially an image, or maybe through vectorized information, like vectorized polylines? Up to you. And then there is yet another dimension, is that of the dependencies across modules. So for example, should the occupancy prediction directly depend on motion prediction? Maybe yes, maybe not. So there was no systematic way to explore this huge space. So what we've done with my group, a paper that we published last year at the CVPR, was to build a tool that essentially proposes a computational graph framework to model the task of driving. So basically, with this framework, we can investigate the necessity of the module, its placement, or the representation of information. And we carried out an exhaustive study in terms of all possible different combination of things. And the end result is somewhat surprising and quite interesting. So it turns out that a fully parallelized architecture, which we refer to as a paradigm, seems to be the best one in terms of performance. So what do I mean by a fully parallelized architecture? So this is an architecture whereby we have raw input information like images that are processed by a shared transformer backbone that produces outputs in parallel for core AV tasks, maybe mapping, motion prediction, occupancy prediction, and motion planning. So this architecture follows the philosophy of train heavy and infer light. So training time, all the heads, so all the outputs are necessary and crucial as a co-training them, embeds in better shapes the latent space to reflect key driving tasks, such as, for example, mapping and occupancy prediction and so on. But then at inference time, the only output or only head that you can to infer through is the motion planning one. So actually you gain computational speed because you don't have to go through the other heads. So we show that with this architecture, basically we are safer and we're also faster computationally. And of course, if you want, you can also exercise the other heads at runtime if you wish. but maybe at a lower frequency, for example, to do consistent checks in order to assess the integrity of your operations. So importantly, this architecture is built from the ground up to be integrated with the foundation models. And in particular, we consider a parallel architecture whereby one of the auxiliary tasks is that of video generation. So at training time, we could train on motion planning, object detection, and video generation. Of course, we don't care about generating videos when we drive. We only do video generation because this task forces the model to build a powerful visual representation of the task of driving. And then at runtime, we only exercise motion planning and occasionally object detection for confidence view and for safety checks.
Good question. So during training, so when you run object detection, is it used for motion planning?
No, this is parallel, yeah.
And then what are you thinking?
You could. I mean, we show in our experiments that it's actually better to do it this way. But, there were some limitations in our experiments. For example, the way that we carried out the design study was to only look at open loop metrics. And of course, there is a difference between open loop and closed loop. So it's possible that potentially, from the perspective of closed loop metrics, the paths where you feel object detection and motion planning could be better. Maybe yes, maybe not. But for now, actually, this architecture seems to work quite well. I know that it's a bit counterintuitive because typically the way we do it is with object detection that is informed motion planning. It does is informative because, of course, when you're training, you teach the model how to do object detection. So you have a latent representation of what object detection is that is then used by motion planning. So that's the point. This is to basically implicitly encode this knowledge. A little bit how you, for example, as a human, you're able to detect objects. But when you move around, you're not really explicitly detecting objects. You're using that information implicitly to inform motion planning. I mean, this is a very, of course, anecdotal explanation.
Got it.
But that's at least the way I would interpret it.
Everything's in the backbone.
Yeah, at any time, this information is pushed back in the backbone and then it's in time.
Right, that's the idea.
So we tested this stack in a simulation in our nerve-based simulator that I showed you before. It seems to be sensitive. So that gave us confidence to test it on the car. So that's what we did. And now we're driving around Santa Clara with this stack, and we drive like a full hour without these engagements. So for example, here we're driving to this kind of foundation model power end-to-end model. So here we are actually driving close to NVIDIA headquarters. Oh, that's NVIDIA headquarters, by the way. It's Santa Clara. So yeah, so and it's fast and it's quite powerful, and especially it was important to see how quickly we can ramp up on the KPIs with this type of architecture, because now the ceiling is represented by the amount of data that you have. You're not really putting constraints with your human-derived heuristics. So this is one of the very first cases of having a video generation Coulter model running on the car. And this was back last year. So this year we have been scaling this up, and we'll also add language retraining and then a chain of thought reasoning and so on and so forth. Maybe next year we'll have that. I'll tell you more about that. So now to conclude, I'd like to talk a little bit about safety. So as I said, people have concerns about safety with these models, partly so. But my point here is that foundation models are not that magic. So they are data-driven models, albeit very large one. How large? Well, for the model that I showed you, that was a 1 billion parameter model. We also have distilled down models at the level of 500 million. So they're not humongous, but they're still large models. But the automotive community, of course, has a strong legacy of fielding data-driven models in the stack. And at the end of the day, the way that I like to think about it is that the confidence, deployment of data-driven models can be achieved by a combination of design time guardrails, deployment time guardrails, and validation time guardrails. Design time and guardrails refer to steps we take in the design and training of a foundation model empowered end-to-end architectures to ensure that the model learns safe behaviors. That's tricky because of course, you want to make sure, since the model is good as your data, you want to make sure that the behaviors that are used to train your model represent a safe driving and not unsafe driving. But what is safety? So how you curate the safe data sets is tricky, so you have to be very intentional. But there are ways to do it, and this is a very, among other things, one of the techniques we use in the context of design time guardrails. Design time guardrails refers to steps we take to keep the AI in check. So basically to equip an AV stack with a runtime monitors that, for example, monitor at the input if a machine learning model is operating out of distribution that is on data that is too different from the one seen at training time. And therefore, you should have any confidence that the model is trustworthy, or runtime monitors at the output, or even a physical guardrail. So basically, subsets of the state space within which your end-to-end model is allowed to drive. With understanding that as you are approaching the boundary of that set that can be computed, for example, with the distributed theory approaches, then you fall back into a contingent plan. And validation, of course, is crucial. And again, there is no silver bullet there. It's a combination of techniques to measure safety, to level operational design domain, and so on and so forth. I could spend an entire talk on this topic, but what I want to focus here is an aspect that is a bit overlooked in the community, that is that of how foundation models can actually improve the safety of an automated vehicle. And there are different ways they can do so. For example, in the context of the design part of the V model, we can use foundation models to build more powerful monitors, or a validation time foundation models can be used for data activation, for example, to auto-level behaviors that are deemed safe, or for evaluating the safety of a model, or, for example, to generate scenarios, as I showed you before. Here I want to talk a little bit more about runtime monitors. And to motivate this concept of foundation model and power runtime monitors, let me show you a display of a Tesla. So what you see doesn't make any sense. We have traffic lights that are spawned by a truck. But now you understand what's happening. That's the example at the beginning. You do have a truck that is transporting traffic lights that are interpreted as illegal traffic lights and cause ghost brake on Tesla. And here is another example where there is a customer that is angry because there is a stop sign that is printed on a billboard for some reason. And then every time his vehicle goes by this billboard, the stop sign is interpreted as a legal stop sign, and the vehicle slams on the brake, which is definitely an inconvenience, but also a safety hazard because the vehicle can be rear-ended. So the point of these examples is that here you can't really say that, for example, the detection algorithm has made any mistakes. For example, here it has correctly identified the stop sign. The problem is that the autopilot lacks enough semantic understanding in order to properly reason about these cases. I refer to these cases as a semantic analysis. So my point is that everything that the vehicle needs is a little bit more semantic understanding of scene in order to address this case. So that's where, again, foundation models can come to the rescue. So to see how we could actually use foundation models in the setting, we recreated the setting of the Tesla vehicle. So there was a vehicle with a traffic light on top. This is in Carla, and our car stopped because thought that the traffic light was a legal traffic light with a red light. And then we use a general purpose open vocabulary object detector that finds, among other things, that there is a truck carrying a traffic light in the scene. And then we use this information as part of a prompt template that we give it to a large language model. But essentially, we prompt the large language model by saying, assume that you are a runtime monitor, explain to the model what a runtime monitor is, And now you have this information. Is what I'm seeing something anomalous? And what we get at the output is kind of interesting. So we see that the model correctly says now a tree is completely normal, no reason for alarm, but a truck carrying a traffic light is an anomaly. And interestingly, it also gives an explanation about why this is anomalous. It says this could deceive the vehicle into interpreting a traffic light as a legal traffic signal. So this is just zero shot, just an emergent product of the learning model that we use, which was quite encouraging. And of course, we have many more cases and more quantitative analysis in our paper. So this seems encouraging, but one of the issues with large language models is that in general, they are slow. So basically, they rely on autoregressive generation of text. And with a runtime monitor, you want to have something that is as lightweight as possible. It should run very fast, and it shouldn't add too much computational footprint to your stack. I think I need to charge.
Yeah.
Thank you.
Yeah, good.
So then we realized, well, oftentimes it's much quicker to realize that there is something anomalous with respect to thinking about what I should do in the case of an anomaly. So we explored the idea of using foundation model embeddings to quickly understand whether there is an anomaly, and then rely on autoregressive generation only to reason through an anomaly. So basically, we're trying to replicate thinking fast and slow type of a term. By quickly, we try to detect if there are anomalies, but something that is less powerful than a fully autoregressed text that is generated by LLM. And then if there is indeed something anomalous, then we query the full-blown LLM. So specifically, the idea is to cache prior nominal experiences in a vector of in a database, and embedding those experiences through a large language model. So basically, we use large language model embeddings, and we store them in a vector database. Then, from new observations that come in online, we can compare the new observation ET to all the ones that have been stored in that vector database. And then we compute a sort of a distance. If the signal exceeds a certain threshold, we declare that there is an anomaly. At that point, we query a full-blown large language model to decide what to do next. So if there is no anomalous, we just continue. If there is anomalous, then we do full autoregressive generation. Question?
Oh, interesting. This is pretty easy, but like efficient. We've never think about it.
Yeah. So the idea is that for the anomaly detector, we just use embeddings. They still retain some notion of semantics because we have large language model embeddings, and we saw good enough. Of course, detecting if there is an anomaly is a much simpler task than understanding what to do in an anomaly. And so we explored the idea, can we just use embeddings to detect anomaly and do full text generation in the case when we have actually to reason about an anomaly? That's in a nutshell what this thing is doing.
Does that mean that we have to see the anomalies before to see that the database?
No, in the database, we only store everything that essentially is captured at training time that is deemed as nominal. And then we look at any new observation, we compare it to what we have stored. And if there is too excessive distance, we deem what we have seen as an anomaly. The point of an anomaly is by definition something that you haven't seen at training time. So we're trying to reason about unknown unknowns. So here is how this works. So with a classical stack, we recreated this example in Carla. There is a stop pointing on the billboard, and then the vehicle will be misled and it will stop. We instead the anomaly detector that I just presented, we do detect an anomaly. So this is something weird. Then we query the full-blown LLM. We see that there is no reason to stop, and then continue. So let me show you more in detail how this works. So we get close to the stop sign on the keyboard, and we query we use the LLM-based anomaly detector, which can run extremely fast. You can see in a matter of a few milliseconds, because we're just comparing embeddings. And now that we have found that there is an anomaly, then we query a full-blown LLM, in this case, GPT 3.5, and the LLM is telling us there is no risk, so we can continue. So now, for this specific example, we achieved 97% true positive rate with an accuracy of 77%. With a false positive rate that is quite high, it's at 54%. But it should be recognized that, first of all, better this than nothing, so making mistakes. But second of all, with a false positive rate, it means that the system is cautious, is over-conservative. So at least we err on the side of safety. Of course, there are many different ways one can extend this line of work. In particular, if you use a higher capacity model, so you go to GPT-4 and so on, you can boost accuracy much higher. Maybe you can try DeepSeek, we haven't tried it yet. But there are many other things that we could be doing that we haven't done yet. For example, we could reason about multi-frame observation. So what we're doing now is just to give one image and asking the model whether there is an anomaly. But of course, to reason about anomalies, the temporal evolution of a scene is a very strong cue. So this is something that we can certainly do, and we should, we haven't done yet. Using foundation models in a more sophisticated ways, for example, using some uncertain information the foundation models provide, and do some data fine-tuning for the model. So for here we have just used zero shot, for example, GPT 3.5, but of course we can fine-tune those models to heavy data. To show you that this works for real, so I'm showing you an example where we run this model on quadrotor. So the quadrotor is flying around, it should land on this box with an orange ceiling. And it's navigating about a clutter of objects and see a keyboard, which is something it's never seen at the training time. So it's wondering, is this keyboard going to shoot missiles? And so it's detected as an anomaly. We query the GPT 3.5, and GPT 3.5 essentially says that the keyboard is not dangerous for a quadrotor, so you can keep going, and that's what it does. So quite interesting, this topics of algorithm distribution detection and generalization. So if you're also interested, that here is a review paper we wrote last year, I think, that basically provides a survey of astronomy of all the problems and a survey of rhythm of works.
Quick question.
Yeah.
So after anomaly detection takes place, then it's very fast. Then how do you decide what to do afterwards?
Yeah, so all of this is orchestrated in a model-related control framework. So basically, this model-related MPC, yes. So this model-related control framework would actually plan by taking into account the delay that is incurred by querying a foundation model, so about 3.5 seconds in this case. And then we have a predefined contingency plans, in this case, basically stopping on the shoulder that we keep visible, even if it is detected that we should stop immediately. In the case of a quadrotor, of course, the contingency plan just will hover in place.
I think the one case is the delay when you query the large language model may take time, and the delay is
about 3 seconds.
Right. 3 seconds may not be suitable for random driving.
Yeah, but because the MPC is trying to keep visibility of the contingency plans at all times, what you get as an emerging behavior is that the vehicle slows down, which is, again, quite intuitive. When you drive, typically you don't pay attention to what you're doing. But then if something is anomalous,
So
all of a sudden,
buys you more time.
you slow down your dynamics to buy more time. And that's what this MPC framework is giving you as an emergent property, basically, by the way, we have said that. So even in those cases, you might have to, it's not super clear from the video, but the vehicle does slow down in order to maintain feasibility for all the contingency plans.
Okay. So you did possible to build sort of like a on vehicle smaller language model.
I mean, language model can drive the vehicle already now on an orange platform. So up to 500 million parameter model.
So what I'm thinking about is instead of querying the large language model, you do it more local.
Yes, yeah, it's local.
It's local.
Yeah, yeah.
Then why it still takes 3-4 seconds?
Yeah.
I see.
But I mean, so first of all, of course, there is a huge spectrum of large language models, and there's a huge spectrum in terms of their size when they are distilled. When saying half a billion parameter, maybe in the future 1 billion parameter model can already be, it can be run basically in real time, even with the delays that are below. Of course, it depends also on how many tokens you want to generate. But anyway, for a decent number of tokens, you can run them in real time. And of course, if you fine tune them to this specific task, you might have even more performance gains. So my point is that running these days a foundation model in general on an edge device is not out of question.
Yeah.
It can definitely be done. And indeed, for example, I don't want to advertise NVIDIA, but the chips that NVIDIA has been producing in the automotive context, or in Thor in the future, are specifically designed to support large language model workloads, both for the onboard stack, but also for the AI cockpit. All the cars in the future will have the so-called AI cockpit, where you would use some small language model, I mean small, several million parameters, but this small model that will allow you to talk to your car effortlessly. So saying, well, here I would like to get a pizza, what are the different options? Can you also look for a parking lot? And this thing is going to interact with you. So you're going to have actually families of language models in the car, some of them for monitoring, some of them for driving, some of them as assistant. For assistant, I mean, people are already deploying them. It's not a question of if, a question of when. Language model for autonomous driving, I think that by now there is quite a bit of evidence that are useful, but still, it will take still a bit of time to put the pipeline. Right, so let me conclude since it's getting late. So 4 main takeaways. So why foundation models, first of all, is not for the hype. There are serious engineering reasons why we may want to use them. In particular, they have the potential to provide a quantum leap in terms of long-term generalization. And second of all, they can empower the full AV program. Definitely the stack on board, but also all the other things that need to be done that typically are not very visible in academia, but are very visible when you go to industry. They happen to develop data stack, data curation, auto-labeling, simulation, all that can be dramatically accelerated by foundation models. Second of all, how do we stand up foundation models for AVs? There is not like the foundation model. There is a family of foundation models, which will be pre-trained on language, to put pre-trained on video generation. They come in a different size as well. But probably, I view video generation models as your ultimate core model that gives you very strong visual representation on top of which you can do training, and multi-model LLMs as your ultimate reasoning engine, if you will. How do we use them in the context of autonomous vehicles? Again, they can be used in many different ways. I show you the potential use as an runtime monitor, or also as part of a backward. And finally, can we safely use foundation models for autonomous vehicles? There are no black magic, they're just algorithm models. So we just have to use the usual safety engineering principles of diversity, evidence, engineering rigor, and so on and so forth. But at the same time, foundation models can actually help your safety case. So they're not just a technology we want to guard against harm, but we can also exploit to improve our safety case. So we end here. Of course, I thank all my collaborators at Stanford and NVIDIA. I'm happy to answer any questions you might have.
Let's thank Professor Pavone for
Yeah.
I'm very impressed by your project, the end-to-end training on the Santa Clara one. So I have 2 questions. The first question is, I want to know how much resource you take to train this model, including what data you use, and also how many computational resources you use.
Is it recorded, right?
They need the recording, yeah. So
I'll give you the magnitude and numbers and numbers. So in terms of big data, substantial amount, say several thousand.
Stop
Well,
recording.
it's okay. Several thousands of hours of AD data.
The data.
AD data.
Mhm.
Several thousands of hours. In terms of compute, we use A100 and several of them. Let's put it this way. Several A100. But I mean, it's not ridiculous. It's not at the level of training a large language model, say in the order of hundreds.
Okay, I see. The second question is for us, the lab in the academia. So we do not have that much resources. So if we want to work on the similar project like end-to-end or foundation model, do you have any suggestions we could?
Yeah. Well, first of all, one has to be careful in the following sense that there are some things that start working well at scale. So one should be careful not to make conclusions based only on a small scale experiment. So for example, the training here is done essentially through imitation learning. There is no in-person learning, at least in the example that we showed. And imitation learning is one of those things that really start working at scale. So in an academic setting, you have to be careful that you place yourself in the right data regime for that particular conclusion. Now, of course, if you really want to train an end-to-end model to perform well, it will be very hard to do it in academia. But there are a number of research directions that are unexplored and can be very well taken by academia, as I'm doing it right at Stanford as well. Like, for example, all the part of safety is a very interesting one. So, for example, how do you reason on multiple frames for runtime monitoring? How do you embed the entire procedure with the statistical guarantees? All are things that can be done with very little compute. It actually requires more thinking. In the context of on planning, so for example, there's plenty of opportunities for research. So right now, the way we typically represent a policy is in the simplest possible way. So we represent a policy as a trajectory. So what your model is trying to do is to output a trajectory that replicates as well as possible the one that is representing your expert data set. But you can represent a policy in many different ways. It could be like a tree. It could be a value function, a reward function, to basically understand better what is the long-term implications of your actions. So that is already a huge space that I think is very important, but it can be done with very little function. Or even at the input. So essentially with these models, we condition about a couple of seconds in terms of past history. And of course, these are talking out type of architectures that have to run in real time. So basically 10 Hertz or less. So you cannot really go at 20 seconds in the past because then your context becomes way too large. So there is then a lot of interesting topics out there in terms of neural long-term memory. So how do you, for many maneuvers, for example, you want to have a long-term memory with a span of 20 seconds. Like, for example, how much time have you spent at the stop sign informs you how aggressive you want to be in negotiating. And this is really a very underexplored topic. So I think these are I could go on and on and on. But these are all examples of topics that are very well addressed by academia. They require very little compute, but significant brain power, and could be extreme. They could move the needle in terms of how things are done. If you want to brute force end-to-end training of a model on an AD data set, I will leave that to industry.
Thank you.
I mean, you might have already sorted this problem out, but I was wondering, how these models change when you use a different type of car. So like, let's say a sedan versus an SUV or almost a truck kind of thing, do your models change depending on like the size of the vehicle and like clearance?
Yeah, that's a great question that actually I haven't addressed yet, nor probably have solved completely. Yeah, actually, so in general, the problem of cross embodiment is a big one in robotics. It's particularly severe for robotics for two reasons. One, because the data that you gather, like for example, human demonstrations, is quite different from the way that a robot moves. For example, the arm is articulated a different way than what your arm is articulated. And of course, once you build a policy, ideally you don't want to apply it only to one robot, but you want to apply it to another robot. And robotic arms, for example, can be very, very different among each other. For cars, this problem is significantly mitigated in the sense that, of course, the trajectories that we record from human drivers are still driven through a car, the same car that is used to deploy your AD stack. So basically, the mismatch is much, much lower, so the cross-embodiment problem. And also, the differences in between cars, assuming that we don't go to trucks, are relatively minor. So at least at the level of dynamics are the same. You have no size-limit constraint, roughly speaking, but that's pretty much it. Of course, you have different dimensions. Can you just go to another vehicle without any worry? No, actually, you have to do quite a bit of fine-tuning as well with vehicle-specific data. But my point is that for in this specific context, is much less severe than the robotics context. So you basically can do, you have to do some work, but you can do it. While in robotics, it's still challenging.
Okay, thank you.
More questions?
But let me add also that with a more positive spin, especially through the lens of foundational models, you can actually use the highly heterogeneous data. So for example, something that many people are considering is you don't need to have data that is specific to your sensor configuration. But for example, you can pre-train on the dashcam data. It's basically videos that have been acquired with just one camera by taxi drivers. But you still need a little bit of fine-tuning data that is specific to your sensor configuration.
So I have one quick question. So I'm very impressed by the performance of power architecture.
Mhm.
So you also talk about the different architecture on system architecture design. So AV, the modular architecture, and also end-to-end, and there's a wide spectrum in between. Can you connect your power architecture to
So this kind of background plus parallel heads is one example of something in between.
That's
So
right.
of course, even in the context of a parallel architecture, there are a lot of things that are that we haven't explored yet. Like for example, do we need video generation or not? Do we need language generation or not? Which comes first, language generation or video generation? Do we want to have an additional head? So there is a lot of variations on the theme that you could consider even in the context of a parallel architecture. Then of course, there is also the part of the input side. So how do you encode all the images? There is a lot of different ways of doing image tokenization. So yeah, the high level seems to be like it's just fairly rigid architecture, but then there is a lot of experimentation you can do in that context.
Right. So your transformer backbone is kind of end-to-end, right? And then you design multiple modules on top of it.
Yeah.
So how do we design the heads? How do we design the heads? Different.
I mean, all the heads are networks by themselves.
I know.
And we could
But how do you design?
Oh, that's what I'm saying.
Yeah.
So it's subject to experimentation. We looked at 3 or 4 different instantiations so far. So the one with the 4 heads, where we have occupancy prediction, we have detection, we have motion planning, and so on. And then the one with 3 heads, where we have video generation, detection, and motion planning. Of course, you always have motion planning. And then now we're looking at the visual language action models, where you also have language generation. So we look at the 3, 4 so far. But yeah, many other are possible, and we're just scratching the surface.
Yeah. Thank you.
One thing, I mean, what I like about these multiple heads is that they also can serve additional purposes. Like, for example, they can be used for confidence view. They can be used actually for safety checks with an asterisk. In the sense that one of the problems with the end-to-end architectures is that you don't know exactly what it's thinking. So if you have a detection head, at least it's telling you what are the boxes in your environment. So that gives you confidence that if it's, placing the boxes in the environment in the right places, your planning ahead is, thinking right. With an asterisk though, because, and we haven't done it yet, one should do a more principled statistical correlation between what the, for example, the detection head is doing and what the motion planning head is doing to actually find that there is a causal correlation between the detection head and the planning head, because it's not by design. We have to see empirically whether that is the case. To really say, oh, because it detected the object, it means the motion planning is good.
Thank you.
I have a question regarding model validation on safety issues. So you said that with the large language models, for example, you can detect semantic anomalies, I think it was called, but there's only, so my data set I'm testing, my algorithm on is just limited, but there's an infinitesimal amount of scenarios I could encounter in all the edge cases that could happen. Is there, like, with this new technique of the large language models, a real proof that I can handle all these situations, or how can I prove the validity or the safety of my system in all circumstances?
No, it has to be clinical. So what the large language, the foundation model is giving you is the opportunity to think out of the domain, thereby increasing the safety of your system. But that doesn't help you with the, you still have to prove that that's the case, right? And that has to be clinical. That depends a lot on the type of system that you are trying to deliver. Like, for example, if it is I2++ hands-on like Tesla, you have a given mean time between failure. If it is I2++ hands-free, then you have even larger mean time between failure. If it is L3, it is even larger, to the point that you can't really validate it because you require hundreds of millions of hours to drive. So basically 100 cars starting for 100 hours. So what do people do? Redundancy. So basically you have an end-to-end model, and maybe you have a more classical stack running alongside, cross-checking the two, so that basically you can decompose your safety KPI into two stacks. And since probabilities multiply, you can have a much lower requirement on each one of the stacks, and when you multiply the two in terms of failure probabilities, you reach your requirement. So yeah, so in terms of validation, it has to be empirical, but the hope, and it's the hope because I don't think anybody has done it yet, is to potentially use a simulation to help with your validation case. But of course, the problem is that if you want to use simulation for validation, you have to validate your simulator. So do you trust the KPI that your simulator is giving you? Which basically means that the first time that you deploy your stack, you had to drive your roughly 20,000 hours or 30,000 hours, depending, of course, on the product offer. But then you can use those hours potentially also to validate your simulator. So actually, if you can find statistically that your simulator KPIs are very correlated with the on-road KPIs that you found, that you determined, then the second time you deploy your system, you can now use the simulator that has been validated to accelerate. You're always going to need some real-world driving. But what I'm saying is that the future, OTA things might leverage simulation.
Great.
So in fact, some work we're doing is on validation of simulators.
Yeah, let's thank our speaker again.
All right, thank you very much.
Thank you, Stan, as well.
Thank you. Yeah, thank you for having me.